This is Daryl with Cisco Hands-On Training. Today is the 24th of January 2009, and we're going to move out of routing into switching, and we're going to discuss how Ethernet works and how the address resolution protocol works. Again, my website is www.ciscohandsonttraining.com, and I would appreciate if all of you link to that. In fact, one of my ancient 2500 routers died, and so by linking to this, you increase my Google hit rate and my Google ad revenue, and maybe I'll actually make enough money to buy a replacement router. I also have my feed, but the easiest way to subscribe is just go into iTunes and search on Cisco Podcast, and the Cisco Hands-On Training Podcast will be one of the top 10. So far, we've been talking about IP version 4. It's a protocol for putting data into a packet, and that's the whole goal of networking, is to get data to the destination. The packet needs to be transported on something physical. That could include copper, it could include fiber, it could include radio, it could include microwaves. But when we write the protocol, when we create the protocol to transport the data, we don't want to change the protocol every time we change the physical layer. Back when I was in college, Ethernet was running over coax cable, or the network was running over coax cable, and now it's running over a twisted pair and cable, and it's running over fiber. And if we had to change the protocol that all applications on the internet run on every single time we wanted to change the physical layer, we'd never get anything done. So the solution is to have a different protocol for each physical medium, and then IP version 4 runs on top of those other protocols. So IP version 4 deals with how to get data into a packet, and then these other protocols, of which one family is called Ethernet, is used to get those packets onto a physical medium, like an Ethernet cable or a piece of fiber or a radio wave. Let's talk about Ethernet for a bit, and I'm going to the Wikipedia here, which has an excellent article on Ethernet, and frankly, I think it'd be good for you to just go to Wikipedia and read the article. Here's one physical media. This is this is an RJ45 connector at the end of what is probably what's called a Cat5 Category 5 twisted pair, which is good for running Ethernet at 100 megabit and gigabit speeds. And that's one Ethernet one of the Ethernet protocols is designed to run Ethernet over this type of cable. And there are other types of cables. Here's an ancient Ethernet adapter. This was running on coax. Over here we have the twisted pair connector, but over here we have an old coax connector, which would be the old 10-base-2 specification, where you'd run Ethernet at 10 megabits over up to 200 meters or 185 meters or something. Ethernet originally acted as a bus, a shared medium. So, for example, years ago in a university, we had a coax cable running through a department, and we'd run Ethernet over that. And if any of the hosts in the department wanted to transmit, then it would just transmit the data. If two hosts tried to transmit at the same time, then the data would collide on the wire and it would get garbled, and neither of them would have successfully transferred the data. So Ethernet uses something called carrier sense multiple access collision detect, which is you've got multiple access, each host on the net can transmit at the same time, or whenever they want, and if they happen to transmit at the same time, you'll have a collision, and the Ethernet cards are designed to detect that a collision has occurred, and if a collision has occurred, then the host would retransmit after a random interval. So, let's say you have two hosts and each want to transmit, they each transmit at the same time, they collide, they detect the collision, then they each randomly pick an amount of time to back off, One of them will wait 20 milliseconds, the other one will wait 37 milliseconds, and then they'll retransmit. And because they're backing off a random amount of time, it is unlikely that they will attempt to transmit simultaneously the second time. As a result, the Ethernet frames eventually get onto the Ethernet wire and get to their destination. Now, of course, since it's a shared bus, if you got 100 hosts on this shared bus and they're each trying to transmit a lot of data, and the total bandwidth of the shared bus is 10 megabits, as it was years ago, many hosts would saturate. If you had many hosts on that net, you'd saturate the shared bus. You'd end up having collision percentage rates of 30%, 40%, 50%, meaning that half the time you're trying to send data, or half the time it's available to send data, a collision is occurring, and eventually the network's performance would become unusable. The other problem with the old coax Ethernet is that the coax is running from host to host to host through a department. So imagine a big room where you have computers all around the edge of the room, and you have one coax cable running around the edge of the room and going from host to host to host. Now let's say the network just stops working. Well, why did it stop working? It could be a problem anywhere along that cable. So you have to go along that cable and try to find the physical problem. And typically what you'd do to debug issues like that is you'd break up the cable into segments, and then you'd see if each segment works, and eventually you'd narrow down the problem. It's horrible to debug. So how do you solve this? Well, the first way you solve the physical problem is you replace you get a device. They invented a device called an Ethernet hub. An Ethernet hub is a device that goes in the middle of the room, and then you run cables from that hub to each device, and that way each host would have a cable dedicated to it. So you end up spending a little bit, you end up spending more on cabling, but hubs supported cheaper cabling, twisted pair, for example. So you'd have twisted pair going from a Cat 3 twisted pair, and then eventually Category 5 twisted pair going from the hub to each host in a star. And that way, if you had a cable problem, it would affect only one host, and you'd be able to easily identify which host has the problem and just replace that cable. Your cabling was cheaper, and it was easier to manage. But a hub is still a shared medium. It receives a Ethernet frame on one port, and it retransmits them. It retransmitted out all the other ports, and so any two hosts transmitting at the same time can still cause a collision. The next invention was called a switch, and a switch looked just like a hub, and that was beautiful because you take your hub and a switch would look just like a hub. It would still be in a center of a star topology in the room. You'd have Category 3 and then Category 5 twisted pair cabling running from by twisted pair cabling. Here, let's go back to this picture. This is an RJ45 connector, and then inside here is typically twisted pair cabling. The wires are twisted together, so that way the electromagnetic interference from nearby power cables or something like that will tend to cancel itself out. And so it's a nice cheap way of making cable which is unlikely to be interfered with by electromagnetic interference without putting shielding around it or anything like that, which gets pretty expensive. So these types of cables that you've all seen around, that's twisted pair in there. Okay, so you had your hub. Your cabling was in a star, and you had performance problems because the hub is still a shared medium and you're getting lots of collisions. What do? You replace it with this newfangled device invented by a bunch of startups called a switch. And what the switch would do is, if it received traffic, it would run each port as its own separate Ethernet segment, and so that way it could transmit and receive simultaneously on each of the ports connected to the switch. So you might have a 24-port switch, and you could be transmitting to the 24 different hosts and receiving from the 24 different hosts simultaneously on the switch. So you've increased your bandwidth by a factor of 48 maximum in theory. That's really cool. The switch would do is it would receive the traffic from one host, and then it would selectively transmit that out the other port necessary to get the traffic to the destination. We'll talk about how it chose which port to transmit the traffic out of in a few minutes. On each port on the switch, if it can transmit and receive simultaneously, that's called full duplex. If it can transmit or receive on the port, then that's half duplex. Now, even though the switch can has each port dedicated to a particular host, you can still have congestion. If you have 2 or 3 hosts on the net on the switch that are talking to the same server, and they're each talking to each of the hosts is talking to the server at, say, 50 megabits, and it's a 100 megabit switch, then on the port that's going to the server, you're trying to get 150 megabits through a 100 megabit port, so you can still have congestion. But that's an awful lot better than the old days where you'd have a 10 megabit hub, or there were even some 100 megabit hubs, but generally most of the 100 meg are switches now. And so you get vastly improved performance with the Ethernet switch. And again, your cabling is easier to troubleshoot because if you have a cabling problem, it's affecting one of the 24 links as opposed to just taking down the whole room. Now, an Ethernet has its own set of addresses, and in order for Ethernet to work, you need an address, and they chose a 48-bit address. Ethernet, it's called a MAC address, a medium access. I don't know what MAC stands for. It's sort of like it's also called a hardware address. It's 48 bits long. They're globally unique. Each company goes and buys MAC addresses at a nominal fee from a central authority, and the first 24 bits are registered to the company, and you can actually look them up. And the second 24 bits are assigned by the company to each specific interface. So Intel, for example, makes a lot of Ethernet adapters, and they'd go and they'd buy these ranges of Ethernet MAC addresses, and they'd make sure, so the first 24 bits would be assigned to Intel, and then Intel would produce millions of Ethernet adapters, and each one would have a separate MAC address, which is globally unique. No 2 Ethernet adapters on the planet are supposed to have the same MAC address. Okay, great. We got a protocol. We got a protocol called Ethernet, and let's look at the Ethernet frame format. And here is the Ethernet frame format. It is not very complex. You have the destination MAC address, which is the MAC address of the host that you want to talk to. You have the source MAC address, your own MAC address, and then you have an Ether type. There were a couple different types of Ethernet. That's the Ether type identifies what is in the data that is next. 0800 means IP version 4 is the data. And then here's the data, and then there's a CRC checksum at the end just in case your wire is causing something to be garbled. That way you'll detect that the checksum is wrong and you'll throw the bad frame out. So this is simple. This is about as simple a protocol as you can get. Your destination MAC address, your source MAC address, what type of data is in the side, and your payload, which is the actual data, which is usually IP version 4 these days, and then your checksum at the end, which just to make sure it's not garbled. That's all this protocol is. Okay, well, here's a problem. We have a packet that is destined for host 10.0.0.2, which is an IPv4 address, and we need to deliver that on the Ethernet. Well, in order to deliver it on the Ethernet, we need to know the Ethernet address of the other end of the we need to know the Ethernet address of the host at the other end, and we don't know it. All we know is host 10.0.0.2 that we probably got from, we probably go into www.something or other, and we looked up www.something or other in DNS, and we got the destination IP address, assuming we're actually on the same net as that host at the other end. We need to deliver the packet on the net. We need to know the Ethernet address. The solution is to use the address resolution protocol. The address resolution protocol uses an Ethernet broadcast. Basically, it sends a special Ethernet frame with a destination MAC address of all Fs, which all Fs in hex, so every bit is set in the destination MAC address. And Ethernet knows, hey, that's a broadcast. It gets delivered to every host on the net, and it says, the ARP says, who is 10.0.0.2? And then the host that happens to be 10.0.0.2 will respond saying, I am 10.0.0.2, and here's my MAC address. Let's take a look at ARP at work. So here I am on a host, and I have config, and you can see that my IP address, IP version 4, is 10.1.1.3, and it's a /24 net mask. And also you can see here's my Ethernet address, 002241. Let's go ahead and try something here. Let's go ahead and search in Google OUI identifier. And here's the IEEE registration authority, hit number 1, and here I can search on a MAC address. So let's search for 00-22-41 search. And you can see that these are the first 24 bits of a MAC address, and it is registered to a company which makes the Ethernet adapters, and the company it's registered to is Apple. And that makes sense because this is the built-in Ethernet address on my Macintosh. So just from an Ethernet address, if you see an Ethernet address that's doing something wacky on your net, you just do a Google search on OUI identifier, and hit number 1 will allow you to search on that MAC address, and the first 24 bits will tell you the manufacturer of the Ethernet, which may be a clue as to what type of device is malfunctioning in your net. Okay, so I have config, I have an IP address configured, it's a /24, ifconfig also shows me the MAC address on the box, and ARP-A shows me the MAC address of another host on the net. And let's sudo ARP-D. Let's do a sudo ARP-D 10.0.1.1. Okay, and it deleted the ARP entry. And now it figured out very quickly that 10.0.1.1, it was once I deleted the ARP entry with the ARP-delete command, then my box, it needed to know how to get to that IP address again, so it sent a new ARP request, which I missed. So let's do a sudo TCP dump -p proto ARP. Sudo TCP dump ARP. So here I am, I'm looking for ARP requests on this net, and then in another window off screen, I'm doing a sudo -d 10.0.1.1. Oh, I'm sorry, sudo ARP-D 10.0.1.1. I deleted the ARP entry. Okay, I made a mistake, and my mistake was that I deleted an ARP entry on Ethernet 1, which is my wireless interface, and I'm actually on the net 10.1.1.1 for my Ethernet 0. Up here you can see Ethernet 0, my IP is 10.1.1.3, and down here in Ethernet 1, which is the wireless net on this box, which actually goes to my wireless router and over to the internet, is 10.0.1. So, okay, so I'm actually on the 10.1. I'm actually at 10.1.1.3, and I went ahead and I pinged 10.1.1.1 while I was running a TCP dump ARP. And you can see here is the ARP request. ARP who has 10.1.1.1 tell 10.1.1.3, and then the host at 10.1.1.1 responded saying, I am on the net and here is my MAC address. And you can see the MAC address, the first 24 bits is 00000C, and this TCP dump program is actually smart enough to know that the first 24 bits of those are allocated to Cisco, and is actually helpful enough to print it out. If I wanted to go back to that website and type in 00000C, you could see that 00000C, the first 24 bits in hex of the MAC address, is registered to Cisco systems. And that makes sense because this device at 10.1.1.1 is one of my surviving Cisco 2500s. Now, this wasn't really enough data to be interesting, so sudo TCP dump ARP. Let's do sudo TCP dump -v -x ARP. And I have 10.0.1.1 in my ARP table right now, which I print out with ARP-A. And so let me delete that. So I will do a sudo ARP-D 10. Actually, I'm making the same mistake again. I want Ethernet 0, 10.1.1.1, and I will hit return off screen. And now I'm doing nothing because I don't need to talk to 10.1.1.1. Now on off screen I will ping 10.1.1.1. And the first thing I had to do was do I had to ARP saying I had to do an Ethernet broadcast, which is an ARP, who is 10.1.1.1, tell me 10.1.1.3. And then we got an ARP reply, 10.1.1.1 is at this MAC address. And the only thing that's sad is I'm not seeing the Ethernet headers here, so let me pause for a second. Okay, let me try that again. And according to the manual, -E will print the link level header on each dump line. And let me offline, I deleted the 10.1.1.1. And now let me ping 10.1.1.1, and because I don't know the ARP entry I don't know the MAC address for 10.1.1.1 in my existing ARP table, I will send out an ARP request for it. And here I am. And so again, I sent out a, from my MAC address, I sent something to the Ethernet broadcast, and it printed that out. And the ether type was ARP 0806. So in the so ARP is its own protocol, and 0806 is here in the ether type, which means that it's an ARP request. And the data is it's an ARP request. Who is 10.1.1.1 tell 10.1.1.3, and then here's the response. and the response was was unicast in Ethernet from the Cisco's MAC address to my MAC address, and it said that it's an ARP reply, and it says 10.1.1.1 is at this MAC address. And then, as a result, now if I do an ARP-A, 10.1.1.1 is at this MAC address. So now I have populated my ARP table. So now if I ping 10.1.1.1 again, no change over here, no new ARP over here. When you ARP for something and you get a response, you put it in your ARP table and you keep it there. Okay, so that is how ARP works. You have a packet which is destined for an IP address, 10 dot whatever, and you don't know the MAC address, so you broadcast out on the Ethernet, and the host which goes to the Ethernet broadcast MAC address, which is all Fs, and then the other side will respond saying, I'm 10.0.0.2 and my MAC address is blah. And then you can start sending traffic to that MAC address. Okay, so that is how ARP works, and let's look at an Ethernet switch here for a little bit. So here I am on a switch, and actually here's our map for today. Here I am at 10.1.1.3, and I have a router at 10.1.1.1, and there's a switch in between us at 10.1.1.2. And this switch is smart. If it has a frame which is destined for the MAC address on this router, it tries to send it out this interface here. And if it is a frame destined for this MAC address down here, for the MAC address of this host, it'll try to send the frame down out here. Well, how does it do that? It is something, well, let's look at the switch. Show IP and brief. It is 24 ports, and 2 of them are up, Fast Ethernet 0/1 and Fast Ethernet 0/2. And they're all in VLAN 1 because I haven't configured anything on this switch yet. Let's look at show Cdp Neighbors. And you can see out Fast Ethernet 0/1 is the router, which is a 2511. And there's no CDP entry out Fast Ethernet 0/2, and that's because my Macintosh is out 0/2, and the Macintosh does not speak CDP. Okay, so let's show MAC address table. And there are 2 MAC addresses of interest here. One is, remember this is the Cisco, and it knows that the Cisco is out Fast Ethernet 0/1. How does it know that? It knows that because this Cisco sent a frame previously, and when it sent the frame, this switch saw that out this port it received a frame, and the source MAC address for that frame was this MAC address. So since the source MAC address out Fast Ethernet 0/1 started with 00000C, then the switch entered that into its MAC address table saying, hey, if I want to get to the MAC address starting with 00000C 477421, I will send that out Fast Ethernet 0/1. And if, likewise, the Macintosh previously sent a frame, and the Macintosh sent the frame with a source MAC address of 00224127A40A, and it was received by the switch on Fast Ethernet 0/2, so the switch entered that into its MAC address table. So now the switch has 2 entries in its MAC address table. And it, that way, if it needs to send if it has a frame and it needs to deliver it to this MAC address, it will send that frame out only Ethernet 0/2, which improves performance because you're not wasting bandwidth on other interfaces. Now, on the other hand, if you have a frame that's destined for some other MAC address that's not yet in your MAC address table, then the switch will attempt to emulate the previous behavior of the hub, which is it will forward that out all ports. And that way Ethernet will work as it always worked for the initial communications, before the MAC address tables are populated, but the switch over time learns which port each host is out of. And by over time it learns that, I mean very, very fast. If the hosts are talking to each other, then the switch is going to figure that out really quick. So clear cam. Let's clear the MAC address table for all dynamic MAC addresses, dynamically learned MAC addresses. Show MAC address table. And you can see already, even though I cleared the MAC address table, one of the ports has already been the host to the Cisco. It's already detected the MAC address. So the Cisco already happened to send a frame with that source address. Let's look again. Nothing else. Now I'm going to go and ping 10.1.1.1 from the host. And I can ping, and now let's look at the MAC address table. And there you can see that once I pinged, as soon as I originated some traffic with the source MAC address of my host, the switch figured out that I was out fast Ethernet 0/2, and it populated the MAC address table. So we got two tables here that we're dealing with. The ARP table is a record on a host which says for this IP address, its MAC address is here. So when you're first trying to communicate with an IP address, it will broadcast a request saying, hey, what's your MAC address? And then the other host will respond via ARP, and then you populate your ARP table on a host. That's different from the MAC address table, which only exists on switches. And the MAC address table on switches is this MAC address is out this port, and that MAC address is out that port, and that's to improve performance. Now once the switch has an IP address, if it's talking to something, so like conft int VLAN1 IP address 10.1.1.2 255.255.255.0 no shut. So I do a show ARP, and the only ARP address I see, or the only address in my ARP table that I see is my own MAC address. Show int VLAN1. You can see if I do a show int VLAN1, here's my own MAC address here. Well, 0018BA is what it starts with. And up here, 1.1.1.2 is 0018BA. It's my own MAC address. And show ARP. Now if I ping 10.1.1.1, I ping successfully. Now I look at my ARP table, and you can see what really happened is I did an ARP request and got a response. And then I populated my ARP table. Now let's do a debug ARP. And now let's ping 10, let's do a show ARP. And again, I only have the two entries, my own and the Cisco's. And now let's ping 10.1.1.3. And here's the debug information. And the Cisco switch needed to send a packet to 10.1.1.3. It did not have the MAC address of 10.1.1.3, so it created an incomplete entry in its ARP table, and then it sent a request from 10.1.1.2 to for 10.1.1.3 with an Ethernet broadcast address, and it's saying the Ethernet broadcast address is all zeros here. And then it received a reply from the Macintosh saying, hey, I'm 10.1.1.3 and here's my MAC address. And then, show ARP, it populated its ARP table with that information. And it has a timer. It'll time out the ARP entries after a certain number of minutes, and I don't know exactly what that is offhand. Okay? So that's the ARP, so this switch, because it has an IP address and needs to talk to other IP addresses on the net, it has an ARP table, and it also has a MAC address table, which shows which ports, which physical ports each MAC address is. So when it's forwarding a frame, it can intelligently forward it just out this port to save bandwidth. And if it is a frame which it does not know, it does not have a MAC address table entry for a particular MAC address, then it'll forward it out all ports because that emulates the hub behavior. Okay, so that is how ARP works, and that is how Ethernet switches work. And that's it for today.